Earlier we have used different kinds of semiconductors, but particularly we have mentioned silicon because of its various properties for the IC fabrication technology. Now, we shall discuss about different types of semiconductors, and in the first phase of this lecture I shall come across different types of semiconductors, namely the 3-5 compound semiconductors. In 3-5 compound semiconductors, basically these are basically the gallium arsenide, gallium phosphide, gallium nitride, aluminum arsenide, indium antimonide, indium arsenide and indium phosphide. So, one of these elements say belongs to the group 3 of the periodic table and another group 5 of the periodic table. Say if we take the example of gallium arsenide, gallium belongs to group 3 and arsenic belongs to group 5, or say aluminum arsenide or say indium phosphide, indium belongs to group 3 and phosphorus belongs to group 5 of the periodic table. So, these compound semiconductors has some unique advantage over the silicon, particularly in the area of optoelectronic devices, and both in as a light emitting diode and as a detector. This the advantage of these materials are that these materials crystallize with a relatively high degree of stoichiometry, and it can easily be obtained N and P type. If you consider various type of semiconductors, you know that silicon which is doped both P and N type, because in a device particularly for making a diode or transistor or FET or MOSFET, basically it is a P-N junction diode, and so both type of carrier is required for making the device. So, in that sense that it can easily be obtained both N and P type, and it has direct energy band gaps, particularly gallium arsenide, indium arsenide, indium phosphide and indium antimonide, they have direct band gap. So, let me very quickly refresh your memory that there are two types of band gaps. One is the direct band gap semiconductor, where if you plot the band in the EK diagram, E versus K, E in the y axis, K the wave vector in the x axis, which is nothing but the carrier momentum, then you see that when the conduction band minima and the valence band maxima, they lie on the same K value, say it is K equals to 0, then it is known as the direct band gap semiconductor. And in this case, in direct band gap semiconductor, it is very easily they can contribute in the fabrication of the light emitting diode, because of the same momentum. And now, if you plot the indirect band gap semiconductor in the same frame, that means E versus K, then this has different K value, the conduction band minima or the valence band maxima. This conduction band minima and the valence band maximum, they has different K value. Say it is equals to K equals to, it is K equals to 0, it is K equals to K dash. So, now what happens that normally when electron moves from the valence band to the conduction band and then they again come back to recombine with the holes in the valence band, electromagnetic radiation is emitted, and this gives rise to the light, which is the basic principle of the light emitting diode, which is one of the most important component in optoelectronics. But in this case, for the indirect band gap semiconductor, because the momentum is different, so conservation of momentum is required. So, first what happens that the carriers from the conduction band come to the trap state or the impurity state, and then they acquire the same momentum and finally recombine with the holes in the valence band for the emission. So, normally this indirect band gap semiconductor is not used, though there are several examples where we use the indirect band gap semiconductor, particularly say the example of gallium phosphide, which is used for or making light emitting diode in the region of red, orange and green. This is due to the impurity adding with the gallium phosphide material. Now, this direct band gap material, this gallium arsenide, indium arsenide, indium phosphide, indium antimonide, they have direct band gap. So, these are the better material for making the optoelectronic sources, and also they have high carrier mobilities. You see that they have high carrier mobilities. This is the mu Si, that is the mobility of the silicon, which is at room temperature 1450 centimeter square per volt second, and you can compare this with the mobility of gallium arsenide at room temperature, which is 9200 centimeter square per volt second. So, it is manifold, the mobility of gallium arsenide is manifold higher than the mobility of silicon. So, we see that obviously that 3,5 compound semiconductors had certain advantages over the silicon for optoelectronic devices. Now, as mentioned earlier, that the applications of these materials are in optoelectronic devices for both detection and generation of electromagnetic radiation. And when we talk about the electromagnetic radiation, you know that in electromagnetic radiation basically it is governed by 1.24 by Eg, the band gap, it is in electron volt, and this gives you the lambda or the emission wavelength in micron. It comes from the relation E equals to h nu, E equals to h nu and nu equals to c by lambda. So, if you put the value of h equals h, the Planck's constant, and c the velocity of light, you will arrive at this relation lambda, that is the emission wavelength, it is equals to 1.24 by Eg, Eg is the band gap. So, for the generation of electromagnetic radiation, it is the light emission from the material, and this is the relation which is the governing factor. So, more the band gap, less will be the emission wavelength. That means, if we go for the nitride semiconductors that I shall discuss today itself, you will find that in nitride semiconductor basically because the band gap is higher than 2 electron volt. So, emission is obtained in the blue or ultraviolet region, or if you take the example of say indium antimonide or indium arsenide, which are the narrow band gap material, and if you put here the value of the narrow band gap material, you will find that lambda becomes the wavelength which is in the infrared region. So, for detection and generation of the electromagnetic radiation, these materials, that means these 3,5 compound semiconductors are very much essential, and also in high speed devices. Now, if you look into the band gap of the material, you will find that say indium antimonide, it has a band gap of 0.17 electron volt. So, if you put 0.17 electron volt here in this relation, you will find that it corresponds to the infrared. And say if you take the example of gallium nitride, for which the band gap is 3.44 electron volt, you will find that if you put 3.44 here in this relation, the lambda will be in the ultraviolet region. So, we can say that in 3,5 compound semiconductors, since the band gap varies from 0.17 electron volt, as small as 0.17 electron volt to 3.44 electron volt for gallium nitride, covering the wavelength range from about 7.29 to 0.36 micron, that is from infrared through visible to ultraviolet. The whole emission range, the whole electromagnetic spectrum is covered from 7.29 to 0.36 micron. And this another important application of gallium arsenide and indium phosphide, these are the two group 3 semiconductor, that they are extensively used for substrates for a wide variety of electronic and optoelectronic applications. Because you know that in device technology, what we do, that we use a substrate and then epitaxial growth takes place by means of metal organic chemical vapor deposition or say molecular beam epitaxial method. So, for that the epitaxial layer must have the same type of lattice constant with the substrate. So, in this case that gallium arsenide indium phosphide, they are extensively used for making the substrates for wide variety of electronic and optoelectronic applications. Then there are some issues also, not that the growth of gallium arsenide and indium phosphide is very easily and it is very simple, not that there are certain issues, and in which areas the researchers or the investigators have been trying to sort out those issues, particularly the complex defect structures in gallium arsenide that has two sublattices and deviation from stoichiometry in compound materials. Now, these are two things. One is the complex defect structures. Why it is complex defect structure? Because in gallium arsenide two sublattices are present. One sublattice corresponds to gallium, another sublattice corresponds to arsenic. So, it is not like silicon or germanium, the elemental semiconductor, where only either silicon or germanium is there in the crystal lattice. And another important thing is that since two materials are involved, there may be deviation from the stoichiometry in the compound materials, that thing we shall discuss here itself. Another issue is that the zinc blende 3,5 compounds, these are the zinc blende structure and have no center of symmetry that we know, and their 1-1-1 direction is crystallographically polar. 1-1-1 direction is crystallographic polar. In such structures, the parallel 1-1-1 surfaces of a crystal segment may have different properties depending on whether they terminate with atoms from group 3 or group 5. Let me give an example to drive this point. Suppose it is gallium arsenide, the blue circles are gallium and red circles are arsenic. So, gallium arsenide, and we will find that they are placed in this manner, there are two sublattices gallium arsenic etc. Now, where the termination, because it is a crystal, so it will continue, and if you terminate somewhere or somewhere in this plane, so depending on the termination with the atoms, so which atoms are there, is it group 3 or group 5, so the properties will be different. So, that is one important thing that must be taken care of, which is not the case in for silicon or germanium. And the deviation from stoichiometry, either gallium rich or arsenic rich material, because it can be gallium rich, it can be arsenic rich. When we talk about gallium arsenide, so suppose if the crystal becomes gallium 0.7, arsenic 0.3, that means arsenic has less amount in this crystal. So, it is the arsenic deficiency or the gallium rich, or in the other case, if we consider that gallium is 0.2 and arsenic is 0.8, also it is the non-stoichiometry, because it has arsenic rich material, it is arsenic rich material, since the gallium is only 20% and arsenic is 80%. So, the deviation from stoichiometry, it can be either gallium rich or arsenic rich material, it affects the formation of edge dislocations and may have different properties depending on whether a dislocation line consists of atom from one group or another. Where it is where is the dislocation line? It consists of atoms from one group or another. One group means from group 3, that means gallium, or another means group 5 or arsenic. So, it is very important that the deviation of stoichiometry affects the formation of edge dislocation, and also some of the properties may be deviated from the original or the intrinsic one. Also, it can have many native defects, and their complexes are responsible for both shallow and deep levels in these compounds. Now, we have also discussed what is deep level and what is shallow level, and let me discuss this thing again to refresh your memory, that suppose it is the band structure diagram, it is the conduction band edge, it is the valence band edge, and say it is gallium arsenide whose band gap is 1.43 electron volt. Now, ideally there should not be any impurity states inside the band gap. However, in actual practice, because of the presence of various types of defects or impurity, there are many levels that can have inside the band gap. If these impurity levels or the defect levels, these levels means it is an energy somewhere inside the band gap, and this level is very near to the bottom of the conduction band, or say it can have very near to the top of the valence band for say acceptor states etc. So, these are the swallow levels, a few milli electron volt. Otherwise, in some cases you will find that this defect level is actually deep inside the band gap. That means, several millivolt either from the top of the valence band or from the bottom of the conduction band, and in this case this is known as the deep level, and these deep levels are not very fruitful in electronic industry. Basically, this deep level act as the act as the killers for the optoelectronic materials, in the sense that it gives rise to non radiative recombination. So, that is why this deep level is not we do not invite this deep level to be there inside the band gap, and this is detrimental for the operation of the optoelectronic device. And so, this shallow or swallow of deep levels that can be due to the native defects or their complexes, it is there for 3-5 semiconductors. And suppose there is arsenic vacancies that act as shallow donors, whereas gallium vacancies act as deep acceptors. So, shallow donors and deep acceptors means shallow donors, it is very near to the conduction band, it is very near to the bottom of the conduction band. This is the conduction bandage, it is very near to the bottom of the conduction band, that is swallow. This is known as the swallow donor. If it is arsenic vacancy, if it is arsenic vacancy, or if it is gallium vacancy, then deep acceptor. So, it is the bottom of the conduction band, and so the deep acceptor must be this type of thing, which is some millivolts or some milli electron volts away from the top of the valence band. And another defect is there, which is known as the intrinsic defects, which is basically the anti side defect, that means arsenic in gallium side. In the crystal lattice structure, gallium and arsenics are there, and if we find that arsenic is there in the gallium side, it is known as the anti side defect, and it acts as EL2 center and gives rise to deep level responsible for semi insulating property of undoped material. This semi insulating property of gallium arsenide is very interesting one, in the sense that because of this EL2 defect, it acts as semi insulating. That means either the substrate of gallium arsenide can be p type, it can be n type, or it can be semi insulating type. This type of 3 types of conductivity is not available in case of silicon or germanium or most of the semiconductors, and the essential feature of this deep level EL2 type of defect, where there is a semi insulating property, it is very important for characterizing the epitaxial layer grown on it, so far as the electrical characteristics are involved. Suppose if we take a n type substrate, suppose it is n type substrate, n substrate of gallium arsenide, and you make a n type layer on it, epitaxial layer, this is also n type, this is also n type epitaxial layer, epi layer, and say its thickness is say a few micron, 1 micron. Then if you want to make the electrical characterization of this epi layer of 1 micron n type grown on n type substrate of gallium arsenide, then the problem will be you will not be able to decouple the effect of the substrate in the electrical conductivity of the epitaxial layer. So, now what to do? Because either you can grow this thing on a insulating substrate, but in that case the lattice matching will not be there, and so there will be many defects at the boundary. So, better use any semi insulating type of substrate. Now, if you use a semi insulating type of substrate, semi insulating substrate, SI substrate of gallium arsenide, and on the substrate of semi insulating you grow the n type epitaxial layer of 1 micron, you will find that because the substrate is semi insulating, the contribution of the substrate will not be there on the epitaxial layer which you have grown on the substrate. So, that is very good feature of the semi insulating substrate, and one can rope on it when the epitaxial layer characterization, particularly the electrical characterization of the epitaxial layers are involved. And these epitaxial layers of these compounds are grown at much lower temperatures than their melting point. That is also very important consideration of this 3,5 semiconductor. Say gallium arsenide, the melting point is above 1200 degrees centigrade, but the epitaxial layers are grown at say 600 degrees, 650 degrees centigrade. So, that is applicable for indium phosphide also, and we know that the epitaxial layers are the most important layers for the device fabrication. All the devices, particularly the devices related to the IC technology, it is made on the epitaxial layers, and for epitaxial layers the substrate is essential for growing the layers. Then another important group of semiconductors which we can discuss is the 3,5 nitrides. So, you see that we have already talked about silicon, we have talked about germanium, then we have talked about gallium arsenide, indium phosphide, that means 3,5 arsenide phosphides. Now, we shall discuss the 3,5 nitrides, that means the gallium nitride, aluminum nitride, indium nitride, aluminum gallium nitride, both the binary nitrides or the ternary nitrides. So, that we shall discuss now. These are wide band gap material. Wide band gap means band gap is greater than 2 electron volt, and since the band gap is very wide, these are useful materials in optoelectronic devices operating in the visible and ultraviolet spectral region. That is very important that it is available in the visible region. If we talk about the gallium arsenide or the indium phosphide or other 3,5 arsenide phosphides, we will find that the visible spectrum emission in the visible region is not available if you use those material for fabricating the light emitting diodes, but in 3,5 nitrides they are visible. Why it is visible? Because if we can show you the relation of 1.24 by Eg, you will find that this Eg, this is the band gap, this band gap is wide in case of the nitride semiconductor, is greater than 2. So, the visible spectrum is obtained, and particularly the blue or the ultraviolet, because the Eg has that kind of a value which will give you lambda equals to 400 micron, 380 micron, 420 micron, the blue or the ultraviolet region. Now, apart from this, that they can emit in the visible and the ultraviolet region, high temperature and high power devices are also important which can be grown on the 3,5 nitrides, and they means the indium nitride, gallium nitride and aluminum nitride, they form continuous alloy system with direct energy gaps ranging from 2 electron volt indium nitride, 3.4 electron volt gallium nitride and 6.3 electron volt aluminum nitride. So, what are these? These are basically 3 nitrides with 3 different band gaps. It is indium nitride, its band gap is 2 electron volt, gallium nitride is 3.4 electron volt and aluminum nitride is 6.3 electron volt, and so one can continuously vary the energy gap values of the alloys made from all these 3 or any 2 of them throughout the visible and ultraviolet region, that will be apparent from this diagram. Say this is aluminum nitride, what is its band gap? You see that the aluminum nitride band gap is 6.3, it is 6.3. Then gallium nitride, its band gap is 3.4, its band gap is 3.4 electron volt, and then indium nitride, it is 2 electron volt. So, that means you can tune the band gap from 2 to 6.3, 2 to 6.3, that means it is throughout the visible and ultraviolet region. So, let me discuss this point in detail, that suppose this is indium nitride, its band gap is 2 electron volt, and then gallium nitride it is 3.4 electron volt. That means, if you make an alloy of these two material, two binary material, suppose the alloy I can write in this manner, that it is indium then gallium nitride, and this gallium indium gallium nitride, you find that when it is indium, when gallium is 0, that means when x is 1, when x is 1, this x is 1, so it becomes indium nitride, and when indium is 0, so x is 0, then it becomes gallium nitride. So, by changing the value of x from 0 to 1, indium x, gallium 1 minus x nitride. So, if you change the value of x from 0 to 1, you can vary, and so that when x is 0, it is gallium nitride and the band gap is 3.4 electron volt, and when x is 1, it is indium nitride, the value is 2 electron volt. So, continuously you can change the value from 2 electron volt to 3.4 electron volt by changing x from 1 to 0. So, that means it is a ternary compound, it is a ternary compound whose band gap is between 2 electron volt and 3 electron volt. So, you can tune the band gap also, and if you can tune the band gap, then you can see that the emission can be blue or ultraviolet or violet, that you can think. Similarly, if you take the case of aluminum nitride, suppose aluminum nitride, its band gap is 6.3 electron volt. So, continuously you can vary, say gallium aluminum nitride, you can vary from 3.4 to 6.3, or indium aluminum nitride you can vary from 2 electron volt to 6.3 electron volt. So, this is band gap engineering that we can discuss separately, but one point that we can see that the nitride semiconductors are essential for the visible spectral region, and why it is essential, because of the fact that it directly related to the storage device. If we talk about the DVD or say high power Blu-ray device, Blu-ray disc, then what we find that their storage capacity is very high, and it is due to the availability of the blue light emitting diode, which is required for reading or writing the data on either DVD or Blu-ray disc. And present generation people use say a red LED, earlier people used infrared LED. So, the storage capacity was almost, the storage capacity in a disc, it is almost proportional to 1 by lambda to the power 4. So, the lambda, if it becomes very small, the storage capacity will be increased, and with very high storage will be there if lambda is small. So, since now present day red is used, earlier infrared was used, and then blue was used, this can be used these days. So, if you find the wavelength, say red is 720 nanometer, 680 nanometer, and blue is 420 nanometer, and infrared is 1000 nanometer. So, if you put the value here, you will find that there will be manifold increase of the storage in DVD or Blu-ray disc, because of the advent of the blue LED for writing or reading the data on the disc. So, in that case the blue is very much important for so far as the storage device, and nitrides are the most promising candidates using which you can grow this blue light emitting diode, and also this blue is very important for white light, because the white light consists of, we know that it consists of RGB, red plus green plus blue, RGB. Now, red LED or green LED is available in the market, with their costing is very less. Now, if one can add the blue, then the white light can be obtained just by mixing the 3 lights, and then what will happen? The important application of the white light will be in our domestic applications or in the street light, where the consumption of power will be very less if you consider with the incandescent lamp or even the lamp which is used these days. So, that is important consideration. So, in that respect, the nitrides are the important candidates or the contenders. Then you see that if you vary this indium nitride, gallium nitride or aluminum nitride, this is on the x axis, it is the lattice parameter because I have mentioned that lattice constant is one of the most important consideration in epitaxy. Then you can consider if it is say A is one material and B is another material. So, the band gap of the material, suppose if you want to make aluminum gallium nitride out of aluminum nitride and gallium nitride, then you can use this formula which is known as the Vegar's law, 1 minus x E g, that means the 1 minus x into band gap of material A. Suppose material A is aluminum nitride. So, aluminum nitride band gap must be put here, and another is x into E g b, that means the band gap of material B, which in our case is the gallium nitride, and so x you can choose for a particular band gap, and this C is a constant, in this case it is 1. So, that means since in this case it is 1, so you can calculate the value of the band gap of the ternary material out of aluminum nitride and gallium nitride. And suppose if you go for the gallium indium nitride, so indium nitride is here and gallium nitride is here. So, if you go for the ternary preparation, then you find that the same thing is applicable. Suppose the material A is gallium nitride, so put the band gap of gallium nitride here, and material B is say indium nitride, put the band gap of indium nitride here, and C is a constant, in this case it is 3. So, very easily one can calculate the band gap of the material, particularly the ternary materials. Then apart from the nitride materials, there are other 3-5 materials as well, say aluminum gallium arsenide, gallium arsenide phosphide, gallium indium arsenide phosphides. So, they are mostly used in fiber optic communication, and proper substrates are important, and I can give you one example that proper substrates means if you want to grow this aluminum gallium arsenide, if you want to grow this aluminum gallium arsenide, this aluminum gallium arsenide, it has to be grown on gallium arsenide. Why? Because the lattice constant, of gallium arsenide is equal to the lattice constant of aluminum gallium arsenide. So, that is a very important consideration that for all values of x, whatever be the value of x, it is lattice matched to gallium arsenide, and this gas L-gas system is used for making the first generation sources for fiber optic communication in the 800 nanometer region. And you see that other material which is gallium arsenide phosphide, it is also lattice matched to gallium arsenide. Then gallium indium arsenide phosphide, it is lattice matched to indium. This gallium X, indium 1 minus x, arsenic and phosphorus, it is lattice matched to indium phosphide by properly choosing the value of x and y. Not that for all values of x and y it will be lattice matched to indium phosphide, not that, but for certain values of x and y this is lattice matched to indium phosphide, because the important consideration of the epitaxial growth is its substrate, and you must choose a proper substrate for making the epitaxial layer free from all types of defects, dislocation, etc. And it is written over here, you see that highly desirable, it is highly desirable to match the lattice structure and lattice constant of the epitaxial layer and the substrate. So, it is also important thing that lattice constant and lattice structure is the basic parameter which one must maintain for making the epitaxial growth. And in that case, that we have mentioned earlier, that this gallium arsenide and indium phosphide, they are extensively used for substrate for a wide variety of electronic and optoelectronic material, because most of the materials, by choosing proper values of the x and y, or the proper value of x, or say the proper values of y, you can grow on either gallium arsenide or indium phosphide substrate. So, in that sense we can say that lattice matching is important. And gallium arsenide, you see that the lattice constant of gallium arsenide, it is 5.65. This 5.65 is the lattice constant of gallium arsenide, and germanium, its lattice constant is 5.65 angstrom, and both the lattice constant is same. So, gallium arsenide can be grown on germanium. So, that is very important thing, that germanium is a group 4 elemental semiconductor, and it is, its lattice constant is equal to, almost equal to gallium arsenide. So, we can very easily grow gallium arsenide on germanium, so that there will not be any lattice mismatch between the substrate and the epi layer grown on it, because of the same lattice constant. And this is very important material, particularly I can tell you that if you take the example of the 3-5 solar cells, indium gallium phosphide based solar cells, the structure is essentially, it is, first you take a germanium substrate or a gallium arsenide substrate, then on gallium arsenide substrate you grow a p-n junction, after buffer layer you grow a p-n junction of germanium, because it is lattice matched to gallium arsenide. So, very easily you can grow without any, free from any defect, the p-n junction of germanium. Then on the p-n junction of germanium above it, you grow the p-n junction of gallium arsenide, and finally above p-n junction of gallium arsenide you grow p-n junction of indium gallium phosphide with indium 0.5, gallium 0.5, actually indium is 0.49 and gallium is 0.51. So, it is okay. And then you will find that there are 3 junctions, p-n junction. One is indium gallium phosphides, its band gap is almost 1.8 electron volt. Then gallium arsenide, its band gap is 1.43 electron volt, and finally the germanium, its band gap is 0.67 electron volt. And you see that it can harness a substantial amount of the solar radiation on it, and it can convert the electricity from the solar radiation. So, this type of a cell is known as the tandem cell, because there are 3 types of junctions, and I have simplified the structure. Basically the structure must involves the tunneling layer, so that there will be addition of the current without any substantial load, and so that the output will be better. And in this case you see that germanium has lower band gap, and gallium arsenide is somehow higher than the germanium, and indium gallium phosphide the highest in this series, and we have to place the top layer with the highest band gap and the bottom layer with the lowest band gap, so that it will be the window for the solar radiation which will be absorbed in the germanium layer. And if you do not use germanium, then what will happen, that substantial portion of the solar radiation and will not be absorbed by this, will not be absorbed. So, harnessing the solar radiation will be difficult, and the efficiency of the solar cell will be reduced, and with this tandem solar cell one can make the efficiency as high as 40 to 48%. And if you compare this efficiency with silicon solar cell, and you will see that the efficiency is almost 20%. So, it is double. So, in that sense we can say that this germanium is very important material because of its lattice constant, which is equal to the gallium arsenide. Then one attractive point of investigation is the gallium arsenide on silicon. Why it is very attractive? Because of the integration, that it is attractive for the integration of optoelectronic devices based on gallium arsenide with silicon circuitry on a monolithic chip, because these all the chips are made of silicon, and those chips are essentially the integrated circuits based on the integrated circuit, where there is no scope of integration of the optoelectronic devices, that means a light emitting diode or say detector or laser, and that is possible if one can make gallium arsenide on silicon, because silicon will give you the better electrical characteristics for integrated circuit IC, because already the process technology and the mature process, because of the mature process technology, it has the most important material for IC technology, and gallium arsenide, it is the most important material for optoelectronics that we have discussed now. So, gallium arsenide or silicon is very important is very important for the investigators, but problem is the lattice constant mismatch, and silicon has a lattice constant of 5.43 angstrom and gallium arsenide has a lattice constant of 5.65 angstrom. So, essentially we find that there is a difference of 0.22 angstrom, and this 0.22 angstrom is very high for the growth of gallium arsenide epitaxial layer on silicon. Why? Because there will be lattice mismatch, and because of the mismatch, high dislocation density will be there in the epitaxial layer, and if there are high dislocation density on the epitaxial layer, then what will happen, that the epitaxial layer the dislocation sites will act as the recombination center for the electrons, and coming down from the coming down in the excited state from the say the conduction band, and what will happen, that they will act as the dislocation centers will act as the killer centers, they will the electrons will be trapped in the dislocation center, and instead of making the radiative recombination, non-radiative recombination will be there, and so we will not get any light. Now, this dislocation density you can reduce if you can match, but for silicon and gallium arsenide it is not possible, but there are some ways people have been trying. How to reduce these defects in such mismatch heterostructures? Why it is heterostructures? Because you see that when we talk about the silicon p-n junction, this is silicon and it is silicon p-n junction. So, it is not a heterostructure, it is a homojunction, because p and n are of the same material. But if we consider that gas all-gas system, that means this aluminum gallium arsenide is made on gallium arsenide, then it is a heterostructure, because two dissimilar semiconductors, it is a junction between two dissimilar semiconductors. So, heterostructures is nothing but a structure or the junction between two dissimilar semiconductors, between two dissimilar semiconductors. So, now this heterostructures and also it is mismatched, because heterostructure, because silicon is involved and gallium arsenide is involved. We are talking about the growth of gallium arsenide epitaxial layer on silicon substrate, and how to reduce these defects, that people have been trying for a long time, and they have come out with the solutions. This selective area growth, another step can be the incorporation of strained layer superlattices and thermal cycle annealing. So, one can try those steps or the pseudomorphic buffer on silicon and can grow the gallium arsenide on silicon, which is very important material for integrating that we have discussed earlier, the integration of the optoelectronic devices with silicon circuitry on a monolithic chip. Then apart from these difficulties of dislocation density, high dislocation density originating from the lattice mismatch, there is other difficulties, and in silicon gallium arsenide case, that presence of residual stresses in the epi layer due to the difference in thermal expansion coefficients. We know that the thermal expansion coefficients or alpha of silicon is different than gallium arsenide. So, if the thermal expansion coefficients of silicon is different than gallium arsenide, what we do that if you grow gallium arsenide with silicon, say at a temperature of 600 degree centigrade is an example, not the actual temperature. So, 600 degree centigrade, what will happen, the expansion of silicon and the expansion of gallium arsenide will be different, because of the difference in the alpha or the thermal expansion coefficient. And then what will happen, that there will be residual stresses. So, because of the stress, it can be compressive or it can be other types of stresses, or say there are presence of antiphase domains. What is antiphase domains? Because this is a polar semiconductor. Which one is polar? The gallium arsenide is polar and silicon is non-polar. So, now we are growing a polar material on a non-polar material. So, we will find that there will be antiphase domains presence in the epitaxial layer. So, if there are antiphase domains, so that will be detrimental for the application of the optoelectronics with that gallium arsenide epitaxial layer. So, because so these are the essential things that we can discuss on the 3-5 semiconductors, and till now apart from silicon or germanium, we have discussed the arsenides, the phosphides, the 3-5 nitrides, and then the some of the band gap engineering type of layered structures like say gallium arsenide phosphide, indium gallium arsenide phosphide, aluminum gallium arsenide, and then one can think of the nitrides, and then gallium arsenide on silicon, gallium arsenide on germanium. It has its own application. So far as the gallium arsenide on germanium is concerned, I have given you the example of tandem solar cell with very high efficiency. Those are used in the satellite communication, not in the domestic application or the terrestrial application, that is for the space application. And even when the satellite is there on its orbital space, the power that is it takes from the solar cell, which is made by the indium gallium phosphide tandem solar cell on gallium arsenide, and below that there is germanium. And also we talked about the silicon integration with the gallium arsenide, because the present day all the chips are made of silicon, and one can make some very good integration with the silicon for making optoelectronics with the silicon integration. Now, we can say that with this knowledge in this type of semiconductors, we can proceed further, and there are many other materials also that we can discuss in due course. And say if we start with silicon, germanium that we have done, and then gallium arsenide and indium phosphide or 3-5 semiconductors, 3-5 that means gallium arsenide etc., that we have discussed today. Then we can start with discussing say 2-6 semiconductors, then 4-6 semiconductors, then say narrow band gap, then wide band gap. So, these are the conventional semiconductors which are mostly the inorganic nature, inorganic semiconductors. and when we shall complete the discussion of all the semiconductors, we shall come across the new type of material which is the organic semiconductor, which is also known as the polymeric semiconductor if the organic is a polymeric one. So, all such materials will be discussed in due course, and each category has its own advantage, has its own disadvantage. Like silicon, the mobility is less compared to the mobility of gallium arsenide, and or the band gap is less compared to the band gap of gallium arsenide. Also it is indirect, it is direct, so it is used for the optoelectronic application. Then we talked about that indium gallium arsenide phosphide or indium gallium arsenide, those are also 3,5 based semiconductors, but this is ternary or quaternary. These are used for the present day fiber optic communication for making 1.55 or 1.3 micron laser for fiber optic communication, laser or LED. So, every category of materials has its own application, and in wide band gap semiconductors we shall see that these materials are very important for high power or devices, high temperature devices, and with very high saturation depth velocity, etc. And organic semiconductor, those are mostly important in case of the large area deposition and coating of the large area for some particular application in the semiconducting area, because the coverage is very high and solution processability. Another important thing is the cost, which is very less. So, those things we shall discuss in detail in the next class. And one thing I must mention at the end of this class is that this semiconductor is important in device application, that we all know. Suppose it is a PN junction or the most primitive, that is a rectifier diode, or say it is a light emitting diode, or say it is a solar cell or any kind of device, say it is FET, the MOSFET, the MOTFET, the HEMT, the MOSHEMT. So, all types of devices, different semiconductors are used, and depending on its particular application or the characteristics it has. And so, for optoelectronics we do not use silicon, because it is we have discussed that it is the indirect band gap material, and also in case of IC technology we do not use silicon. For microwave sources we use gallium arsenide, we do not use silicon. So, because of the high mobility in gallium arsenide. So, those things one must take into account for the application in a particular device area, and different types of materials we shall use. Some of the materials we will find that they are very good in thermoelectric applications, some in the memory type of thing, then there are oxide materials also, zinc oxide, aluminum oxide. So, those oxides, titanium oxide, copper oxide, those are also show some semiconducting property which is unique, and though those are not widely used in all the cases like silicon in IC technology, even then those are very important materials for our application in different fields. Thank you.